This video is an introduction to summing infinite series, and let's just recall the definition from the textbook. An infinite series, sum from n equals k to infinity of a sub n, converges to s if the limit of its sequence of partial sums is s. So that is, the limit as n goes to infinity of Sn is equal to s, where these partial sums are just the sum of the first however many terms. Okay, so let's see what this looks like in a simple example. So if we look at the sum from n equals 0 to infinity of 1/2 to the n, so this is equal to 1 plus 1/2 plus 1/4 plus 1/8 plus etc. And we look at what the partial sums are. Well, the sequence of partial sums well, if we just sum the first term, we get 1. And I'll do these in decimals just so we can see what's happening a little more easily. The sum of the first two terms is 1.5, then 1.75. If we add the first three terms together, 1 plus 1/2 plus 1/4, 1.875, 1.9375, and then let's do one more just so we can see what's going on, 1.96875, etc. Okay, so if we look at this, it certainly seems like the limit appears to be 2. And of course, if we know something about geometric series, as we'll talk about later in the video, we can actually prove that that's equal to 2. But this is kind of formally what's happening here. We're looking at the limit of partial sums, that's a sequence, and then we compute the limit of that sequence, and if that limit exists and converges to s, we say the sum of the infinite series is equal to s. Okay, so let's look at an example of a telescoping series. So if we just look at this series from n equals 1 to infinity of 1 over n times n plus 2, that's not something that just looking at it we kind of know what the sum is. But it does look like something that we've seen in the integration section of this course, and namely, it looks like a partial fractions integrand. So it looks like something to do with partial fractions. So what I mean by that is, if we had the integral of 1 over x times x plus 2, what we would probably do is use partial fractions to split it up and then try to integrate each piece separately. So we'll do the same sort of thing here. So 1 over n times n plus 2, we'll set that equal to a over n plus b over n plus 2, and we'll solve for a and b. And the hope is that this will give us some idea of how to compute what this sum is. Okay, so if we do this, this tells us that 1 is equal to a times n plus 2 plus b times n. And now we want to try to see if we can use this to solve for a and b. Well, if we set n equal to -2 to make a times n plus 2 equal to 0, what will we get here? Well, 1 is equal to a times -2 plus 2 plus b times -2. And now this thing here is going to 0. So 1 is equal to 0 minus 2b, or b is equal to -1/2. And now if we set n equals 0 to make bn equal to 0, what do we get? Well, we get 1 is equal to a times 0 plus 2 plus b times 0. And now that guy is going to be 0. And so we get 1 is equal to 2a, or a is equal to 1/2. Okay, so what we've got now is that the sum from n equals 1 to infinity of 1 over n times n plus 2 is really the same as the sum from n equals 1 to infinity of a was equal to 1/2, so 1/2 divided by n minus 1/2 over n plus 2. And if we write this a little bit differently, this is the sum from n equals 1 to infinity of 1 over 2n minus 1 over 2 times n plus 2. So that's what we want to try to work with now. Okay, so there's what we did on the previous slide. And so let's just try to write out some terms here and see what's happening. So let's write down s sub n. S sub n, the nth partial sum, is what? 1/2 minus, if I plug in n equals 1 to that second term, I have 2 in the bottom times 1 plus 2, which is 2 times 3, which is 1/6. So that's the n equals 1 term. Plus, I'll get then 1/4 minus 1/8. This is the n equals 2 term. Plus 1/6 minus 1/10. This is the n equals 3 term. Plus 1/8 minus 1/12. N equals 4 term. Let's do one more here. 1/10 minus 1/14. That's the n equals 5 term. Plus, okay, so what do we get at the end? Well, let's write out several terms at the end so we kind of see what's happening here. So this is when I plug in, let's say, capital N minus 2, I get 1 over 2 times the quantity n minus 2 minus 1 over 2 times capital N. So this is n equals capital N minus 2 plus 1 over 2 times the quantity n minus 1 minus 2 times the 1 over 2 times the quantity n plus 1. So this is the n equals n minus 1 term. And then finally plus 1 over 2 times capital N minus 1 over 2 times the quantity n, capital N plus 2. This is the n equals n term. Okay, so now let's take a look at this and kind of see what we're left with, and we'll see that there's a lot of cancellation going on. So for example, this minus 1/6 and that plus 1/6 go away. Minus 1/8 and that plus 1/8 go away. Minus 1/10 and plus 1/10 go away, and you can kind of see what's happening here. Basically everything after the 1/2 and the 1/4 is going away. If you kind of go to the end here and try to see a similar sort of thing happening, this minus 1 over 2n and plus 1 over 2n are going away. This term and this term will also go away from previous sorts of things, previous terms that come up. And so what we're really left with is that s sub n is equal to 1/2 plus 1/4 plus a negative 1 over 2 times n plus 1 plus a negative 1 over 2 times n plus 2. Okay? So in the end, what happens? Well, the limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of 1/2 plus 1/4 minus 1 over 2 times n plus 1 minus 1 over 2 times n plus 2. And what's happening with this here? Well, this term is going to go to 0 because we have a capital N in the denominator and capital N's going off to infinity. This term is going to go to 0 as well. And so in the end, this limit is just 1/2 plus 1/4, which is 3/4. Okay, so our original sum from n equals 1 to infinity of 1 over n times n plus 2 is actually equal to 3/4. Now again, I kind of wrote this out formally with the partial sum s sub capital N, but you can kind of see what's happening just by writing out the first several terms if you want to kind of see it informally, that everything but that 1/2 and that 1/4 goes away, and the stuff that's left over at the end, those last couple terms, those are going to go to 0 as n goes to infinity. Right, so let's look at another type of series here that we can deal with pretty easily that comes up a lot in applications, and that's geometric series. So these look like potentially a constant times a common ratio to the nth power. And these guys converge if and only if -1 is less than the common ratio is less than 1. And in the case that we have a convergent series, the sum of the series is the first term divided by 1 minus the common ratio. So let's just look at several examples of this. So first example, let's look at the sum from n equals 1 to infinity of 5 times 2/3 to the n minus 1. Now you notice this has a little bit of a different form from what we have in the kind of general form of a geometric series. The series doesn't have to start at 0. It can start at 1, or it can start at something else. And the exponent doesn't have to be n itself. It can be n minus 1 or something else there. It just matters that the ratio of consecutive terms has to be the same. And in this case, the ratio of consecutive terms is 2/3. If you take any two consecutive terms, that's what you're going to get. So note, for example, if I take 5 times 2/3 to the n minus 1, and I divide it by 5 times 2/3 to the n minus 2, what am I going to get? Well, I'll get the common ratio, which is 2/3. Okay, so this really is a geometric series, even though it doesn't necessarily look precisely the same as the form that we have above. Okay, well, what's the common ratio? It's 2/3, so we know that -1 is less than 2/3 is less than 1. So the geometric series converges. And to what does it converge? Well, we have r is equal to 2/3, and the first term is equal to, so n is equal to 1 in the first term, so 5 times 2/3 to the 1 minus 1 power. So that's 5 times 2/3 to the 0, or 5 times 1, which is 5. And so the sum is equal to the first term, which is 5, divided by 1 minus the common ratio, which is 2/3. So this is 5 divided by 1/3, or 5 times 3, which is 15. Okay, so the sum of our geometric series there is 15. Okay, let's look at another one now that has some negative numbers in it. So here we have the sum from n equals 0 to infinity of -1 to the n divided by 2 to the n. And another way we can write this to make sure we really do have a geometric series here is this is the same as taking -1 over 2, or -1/2, to the nth power. And our common ratio here, r, is equal to -1/2. Okay, well that means that our series converges, right? Because -1 is less than -1/2 is less than 1, so the series converges. And what is this sum? Well, the sum from n equals 0 to infinity of -1 to the n over 2 to the n should be equal to the first term. Okay, so what's the first term? The first term is -1/2 to the 0 divided by 1 minus the common ratio. Common ratio is -1/2 here. Okay, so what's this? This is 1 divided by 1 minus the -1/2, which is 1 plus 1/2, or 3/2, and this is equal to 2/3. Okay, so that series converges to 2/3. Okay, so let's look at one more example now. Let's look at the sum from n equals 1 to infinity of pi to the n divided by 3 to the n plus 2. Okay, so the first question is this actually a geometric series? Even though they don't have the same exponent top and bottom, it really is. You could rewrite this, if you'd like, as the sum from n equals 1 to infinity of pi to the n divided by 3 to the n plus 1. Another way to write that is 3 squared times 3 to the n, right? Because when you multiply there, you add the exponents. So this is the same thing as the sum from n equals 1 to infinity of 1 over 3 squared times pi to the n divided by 3 to the n. which is the same as the sum from n equals 1 to infinity of 1/9 times pi over 3 to the n. Okay, and this thing has a common ratio, r, of pi over 3. Well, pi is roughly 3.14. That's greater than, means this thing is greater than 1. And so we know that the series diverges. Okay, to finish, let's talk about the nth term divergence test. This is a really important test that allows us to tell when certain series diverge. It doesn't ever tell us that a series converges, but it can tell us that a series diverges. And that's that if the limit of the terms of the series does not go to 0, then the series diverges. Okay, so for example, the series that we had on the previous slide, the sum from n equals 1 to infinity of pi to the n over 3 to the n plus 2. And remember what this looks like. We said this is the sum from n equals 1 to infinity of 1/9 times pi over 3 to the n. And if we look at the limit as n goes to infinity of 1/9 times pi over 3 to the n, this is something we know how to deal with from the sequence section. This is the same as 1/9 times the limit as n goes to infinity of pi over 3 to the n, and we know this limit is infinite from the geometric sequence result that we have in the previous section, since pi over 3 is greater than 1. So that sequence, pi over 3 to the nth power, that sequence diverges. Okay, and so since the limit as n goes to infinity of pi to the n over 3 to the n plus 2 is not equal to 0, we know that the sum from n equals 1 to infinity of pi to the n over 3 to the n plus 2 diverges, which we also proved on the previous slide. This is just a different way of doing it. Okay. So another sort of example here that isn't a geometric series, we could look at this series from n equals 1 to infinity of n divided by the square root of n squared plus 4. Okay, and that's not something we really know how to evaluate. We don't have a lot of techniques for this, and so the first thing we might want to do is check to see what happens if we take the limit as n goes to infinity of n over n squared plus 4. And if we do this, let's say we divide through by the highest power of n. So this would be n divided by n up above. And downstairs, if I want to divide by n under the radical, it means I'm dividing by n squared instead. Okay, so I'd get that. And this is now the limit as n goes to infinity of 1 divided by the square root of 1 plus 4 over n squared. And this 4 over n squared is going to go to 0 as n goes to infinity, so this is 1 over the square root of 1 plus 0, which is 1, and not equals 0. So the series diverges by the nth term divergence test. So one final note on the nth term divergence test that I mentioned in the previous slide, but I think is important to write by itself. If we know that the limit as n goes to infinity of a sub n is equal to 0, this tells us nothing about the convergence or divergence of the sum from n equals 1 to infinity of a sub n. We could really have either thing happen. So, for example, if I look at the sum from n equals 1 to infinity of 1 over n, this is known as the harmonic series. this diverges despite the fact that the limit as n goes to infinity of 1 over n is equal to 0. Okay, so the limit of the terms is 0, but the series still diverges. And so that tells us that we really can't prove anything about convergence with this thing. We can only use it to show that a particular series diverges. We'll learn more about, this is a special case of something called a p-series, and we'll learn more about that in the next section. But just to give you another example, if I were to change this to 1 over n squared, this series actually converges, and certainly the limit as n goes to infinity of 1 over n squared is equal to 0. So the nth term divergence test is very powerful because it can rule out convergence for certain series, but it won't ever help you show that a series is convergent.